Welcome to the Deep Dive. Today, we're really digging into something pretty fundamental. How things, well, stand up, and why sometimes they fall down.
Yeah, it's about the incredible ingenuity, but also sometimes the human mistakes behind, the structures all around us.
Exactly. We're doing a deep dive into this really fascinating source, a book that explores materials, forces, design.
Everything from ancient towers to modern planes, even the biology inside us.
Our mission today isn't just to summarize this book.
No, not at all. We want to pull out those key insights, those real aha moments.
See how the same basic ideas pop up everywhere, cathedrals, spider webs.
And uncover the human stories behind the science, give you a new way to look at the world, whether you're feeling overloaded with info or just, curious.
Right. We're trying to connect the dots, make the complex feel a bit more intuitive. So let's unpack this. So the source kicks off with a story, it feels almost.
Biblical.
Yeah, literally. It opens with the Tower of Babel, this ancient symbol of human ambition.
That deep urge to build big, reach high, make a name for ourselves, as the author puts it.
It's a great place to start, isn't it? That mix of dreaming big and hitting the wall of physics.
Exactly. And what's interesting is how the source frames the whole thing as a way to communicate with engineers.
Ah, right. Recognizing that gap between theory and, well, actually making things work in the real world.
Which, let's be honest, a lot of us run into. And the book makes a really good point. You don't need tons of advanced math to get the core concepts.
You really don't.
No. The argument is we're already doing incredibly complex structural analysis all the time.
Like when you catch a ball.
Yeah.
Or just walk around.
Absolutely. Your brain's solving things like differential equations just, intuitively. We've got this amazing analog computer upstairs.
So the difficulty isn't the complexity itself, it's more the formal language.
Often, yeah. Getting past the jargon.
Okay, so if we strip away the math for a second, the basic question the source poses is pretty simple but deep. How do inert things like a brick wall, a rope, a bone,
a steel beam, cathedral stones, how do they actually generate the forces needed to hold themselves up? They're just sitting there.
Right. How do they push back?
And that takes us straight to Robert Hooke, a remarkable figure.
Hooke's law.
That's the one. The fundamental idea that solids have a springiness. His first observation was that a spring's power is proportional to its tension, which back then meant how much you stretched it, its extension.
Pull it twice as far, it pulls back twice as hard. Simple.
Elegant, right. But the real genius step was realizing it wasn't just about the whole spring.
What's happening inside the material?
Exactly. When any structure bends or stretches, the material itself, down at the, what we now know as the molecular level, is stretching or contracting elastically.
That microscopic stretching and squeezing is how it generates the reaction force.
That's the fundamental mechanism, how static objects resist loads.
And it's wild to think that the study of this basic idea, this springiness, was apparently held back for years because of basically a personality clash.
Hooke versus Newton. Yes, the source does point that out. Newton wasn't keen on Hooke, or maybe applied science generally.
And Newton's influence later on seems to have genuinely slowed things down.
It appears so. A real historical speed bump caused by, people not getting along.
So Hooke gave us the big picture. Things act like springs. But to really understand what's happening at a specific point inside the material, you need better tools.
Right. And this is where we hit one of those fascinating gaps in scientific history the source highlights. You had brilliant people, Euler, Thomas Young.
Doing incredible mental gymnastics, the book says.
Yeah, trying to solve structural problems without two absolutely vital concepts, stress and strain.
And Galileo was so close. He spotted that a rod's strength depended on its cross-sectional area.
He did, which makes it almost baffling, doesn't it? That it took nearly 200 years for someone to take the next logical step.
Just divide the load by the area?
Just divide the breaking load by the area. That gives you the breaking stress. And that's a property of the material, not just that one specific rod.
So stress is force per unit area. Pounds per square inch, kilograms per square centimeter, that sort of thing. And the key is, gets a condition at a point. Local.
Precisely. And strain is its partner concept. Strain is about deformation. It's the ratio of how much something stretches or gets compressed.
Compared to its original length.
Right. And because it's length divided by length, a ratio, strain has no units. It's just a number telling you how much deformation is happening, also at a specific point.
And the source credits Baron Kochi with really nailing these down.
Yes, and apparently the French government made him a baron partly for this work. And rightly so, the book suggests. Stress and strain just revolutionized how we could analyze materials and structures.
Okay, so stress and strain let us describe the internal state.
Yeah.
But how do we measure how stiff a material is? The source said Hooke's original law kind of mixed things up.
Yeah, it muddled material properties with the structure's overall behavior. To isolate the material's stiffness, you use a stress-strain diagram.
You test a sample, pull it, measure the force, measure the stretch.
Essentially, yes. You plot the stress you're applying against the strain that results. And for many common materials within their elastic range, you get a straight line.
And the steepness of that line.
That slope is the material stiffness. That's Young's modulus, usually called E stress divided by strain. It's fundamental now, everywhere from physics to engineering, even biology.
It seems so basic now, but the source points out it took until, what, the mid-19th century for engineers to really adopt it widely.
It's another interesting example of how science progresses, sometimes slowly. There was definitely some conservatism among practical engineers.
And the necessary concepts, stress and strain, were also slow burners.
Exactly. And apparently, Thomas Young himself, brilliant as he was deciphering hieroglyphics and all that,
Wasn't the best communicator.
according to a contemporary, he was worse calculated than any man I ever knew for the communication of knowledge. A bit harsh, maybe?
Ouch. So it needed someone like Navier to give the modern definition in 1826 to make it stick.
It seems so. Clear explanation matters as much as the discovery sometimes.
All right, so stress, strain, Young's modulus, we can talk about material properties. Now, strength. The source makes a really crucial distinction here. The strength of a structure versus the strength of the material.
Absolutely critical. The strength of a structure is like the total breaking load for that specific beam or bridge. It depends on its size and shape.
But the strength of a material.
That's its breaking stress, the force per unit area it can take before failing. And that's generally the same for any piece of that specific material, regardless of size.
So engineers use the material strength, the stress value, to predict the structural strength, the load capacity.
That's the goal of strength calculations. And the source has this fascinating table, too, listing approximate tensile strengths.
Yeah, I saw that. You expect steel, wood, but then muscle, bladder, skin, tendon.
Spider silk, human hair.
Tendon is incredibly strong, something like 12,000 psi, and flax even higher.
It really drives home the amazing engineering in biology. Natural materials can be incredibly strong, especially in tension.
Gives you a new respect for, well, how we're put together.
Definitely.
Okay, let's shift from the properties themselves to how they were used, or maybe not used. The source mentions this historical split, particularly in the 1800s.
Ah, the practical men versus the theoreticians.
Right. Especially in Britain and America, there was apparently real distrust of mere theory.
You had engineers like Thomas Telford building hundreds of bridges, solid work, never had a major failure, purely practical experience.
But then you had theoreticians like Navier using the best mathematical models available.
And sometimes their bridges, well, they fell down.
It really highlights the limits of pure theory, doesn't it? Real life is messy.
Totally. Structures can fail in ways you just didn't anticipate. The source calls it the cussedness of things. The weakest link might be the one nobody thought about.
So you need that practical intuition, that feel for what might go wrong.
It's invaluable. And the source notes that 19th century engineers often used what they called a large factor of ignorance.
Basically overbuilding things. A big safety margin.
Exactly. To cover the unknowns, it made things heavier, maybe more expensive, but generally safe.
But even with strong materials and these safety factors, big tension structures still failed unexpectedly. Boilers exploding, ships cracking.
Yeah, the source gives some chilling examples. HMS Cobra, a new destroyer, the liner Leviathan in 1901, both developed massive cracks at sea.
Even though the calculated stresses were supposedly safe.
Right. They managed to get to port, and apparently the incidents were hushed up, but it pointed to a deeper problem.
So what was happening? If the average stress was okay.
This led to understanding the huge impact of tiny flaws. Inglis's work on stress concentrations was key.
Literally around cracks, even microscopic ones.
Yeah, the tip of a crack can be incredibly sharp, down to the molecular level. And the theory showed the stress right at that tip could be massively amplified hundreds, even thousands of times higher than the average stress.
Which makes you wonder, why doesn't everything just shatter instantly?
Good question. It's because materials we use in tension usually have toughness. They have ways to resist these stress concentrations from running wild. But, and this is crucial, the source says, this defense is only relative. Vulnerability is always there.
And this leads to a really important, maybe slightly counterintuitive idea, Griffith's effect.
Yes. The bigger the structure, the lower the average stress has to be kept for safety.
Because there's more chance of a critical flaw or more stored energy to drive a crack.
Both, essentially. It puts a fundamental limit on how big we can safely build things like supertankers or very long bridges using conventional materials.
And the source connects this brilliantly to biology. Bone is brittle compared to, say, tendon.
And the critical length of a crack that will cause a bone to break isn't relative to the animal's size, it's an absolute physical size.
So a mouse can fall much further relative to its size than an elephant.
Exactly. The safety margin against fracture drops dramatically with size. A human or a lion might jump off a table okay. But the source says an elephant has to be incredibly careful, avoiding even small drops.
That's a fantastic example. Same physics, ship steel or elephant bone.
The laws don't change.
Let's switch gears slightly and talk about energy. The source defines it scientifically. Capacity for doing work. Force times distance.
Right, which is different from how we talk about human energy, feeling energetic or tired.
So when a structure deforms elastically,
It stores strain energy, like stretching a rubber band or bending a bow. If it springs back, you get that energy back.
but when something breaks, energy is involved too.
Yes, that's fracture energy, or the work of fracture. It's the energy needed to create the new surfaces when a crack forms and spreads. That energy is dissipated, lost as heat usually.
So looking at fracture now, it's not just about stress pulling atoms apart.
It's an energy balance. Can the stored strain energy in the material be converted into enough fracture energy to make an existing crack grow?
That's the modern view. This source uses the skier analogy.
Yeah, skiers' tendons absorbing massive amounts of energy from bumps cycle after cycle. Tendons are amazing energy stores, reliable, efficient.
And that table 3 in the source, comparing energy storage capacity. Wow. Biological stuff like tendon, horn, rubber.
Way, way higher energy storage per unit weight than metals like steel or bronze.
Tendon is around 2,500 joules per kilogram. Rubber up near 8,000. Spring steel is only like 130.
Even U-wood, famous for longbows, is surprisingly high, maybe 900 J-kilograms. It shows just how optimized natural materials can be for resilience.
Resilience, bounciness. Absorbing impacts. You need flexibility, but also strength.
It's always a trade-off: stiffness, strength, resilience. The source mentions things like Viking ships or old horse buggies being deliberately designed for resilience to flex and absorb shocks.
Which brings us neatly to the bow, an ancient, high-tech energy weapon.
A brilliant way to store human muscle energy, which is generated fairly slowly and release it very quickly into a projectile.
And the English longbow, often made of yew. The source says research suggests yew's structure is almost purpose-built for storing strain energy.
It's a fascinating material, and the way they strung them, the plantanos idea the Greeks knew, bending it backwards first.
That wasn't just to get tension on the string.
No, it pre-stresses the bow limbs. This significantly increases the total energy stored when you draw it fully.
Ah, the area under the forced draw curve is bigger.
Exactly. You might get, say, 170 joules stored instead of maybe 105 joules for the same draw weight, just by starting from that pre-stressed state. Clever.
And the crossbow used mechanical advantage to draw even stiffer bows.
Storing more energy, yes. Good for punching through armor, but much slower to reload.
Compared to the longbowmen at Agincourt, supposedly firing 6 million arrows. A formidable cloud.
Crossbows couldn't match that rate of fire. And interestingly, the source notes the crossbow never seemed to have the same decisive military impact as the longbow, despite its power.
Comparing the energy stored in a bow to, say, a big siege engine.
Like a trebuchet using a falling counterweight. That stores potential energy, maybe 30,000 joules for a large one. But the source calculates you could store that much strain energy in just 10 or 12 kilos of tendon, like in a powerful catapult or composite bow.
So bows and catapults are much more energy dense, weight for weight.
Vastly more efficient energy storage per kilogram.
And this section includes a really vital safety warning.
Yes. Never, ever draw and release a bow or catapult without a projectile loaded.
All that stored energy has to go somewhere.
If it doesn't go into the arrow or stone, it goes violently back into the bow itself, almost guaranteed to break it and potentially injure the archer badly. Stored energy needs a safe outlet.
Okay, back to biology for a moment. Soft tissues. The source says they operate elastically at strains maybe 1,000 times higher than metals or ceramics.
It's a completely different regime, suggests different mechanics. The source mentions they can act a bit like liquid surfaces, with surface tension playing a role.
Leading to spherical or segmented shapes in simple organisms. minimizing surface energy.
That seems to be the idea for things like membranes under constant stress, like in worms.
And most body tissues follow weird laws for stress and strain, except maybe the larynx.
Apparently, larynx tissues are a bit more Hookean, a bit more linear, but most soft tissues have complex, non-linear behavior. Many are composites.
Like elastin and collagen.
Right. A stretchy, low-stiffness matrix, the elastin, reinforced with strong, high-stiffness fibers, the collagen.
Which explains their J-shaped stress-strain curve. Floppy at first, then suddenly stiff.
Exactly. Initially, only the elastin stretches. Then, as the collagen fibers pull taut, the whole tissue becomes much, much stiffer. It's a clever design.
The source also mentions Poisson's ratio again, how things shrink sideways when stretched, and how arteries use internal pressure and longitudinal stretch to manage that effect.
Keeping the tube shape stable under pressure.
Okay, from soft to hard stuff. Compression structures. Masonry, brick, and stone. The source revisits the Tower of Babel calculation.
Yeah, theoretically, a simple brick tower could reach maybe 2 kilometers high before the bottom bricks crush under the weight.
Just based on crushing strength. But real masonry structures, pyramids, cathedrals, they top out around 150 meters. Modern skyscrapers are steel frames, totally different.
So why the huge gap between the theoretical crushing limit and reality?
It's not crushing that limits them in practice.
Nope, it's tension cracking. This happens when the effective line of the vertical load, the thrust line, moves outside the middle third of the wall's thickness.
The middle third rule, attributed to Coulomb.
Right. If the load gets too off-center, one face goes into tension. Mortar is weak in tension, so it cracks. You see cracks in old walls all the time.
They don't necessarily fall down, though.
Not always. The uncracked part might still be stable in compression, but the cracking is the limiting factor.
And historically, builders were figuring this out, like Greek temples with those massive stone beams, architraves.
They often cracked right in the middle from bending tension, but sometimes the crack pattern effectively turned the beam into a shallow arch, which could carry the load in compression, saving the structure. Accidental engineering.
And the Lion Gate at Mycenae? That triangular stone is deliberate.
Seems so. Placed above the main lintel beam specifically to take the load off its center, preventing tensile failure. They understood the problem, intuitively at least, thousands of years ago.
And the source even draws a parallel to aging human spines.
Yeah, likening the vertebrae to stone blocks and the discs to the mortar. As discs degenerate and weaken, they can't handle tension or off-center loads as well, making the spine behave more like a masonry column, prone to issues if the load isn't purely compressive and central.
And besides cracking, columns have another failure mode, especially long, thin ones.
Buckling. Bending sideways under compression long before the material actually crushes.
Let's move from columns to arches and bridges. Arches work mostly in compression.
And the source brings up that creepy nursery rhyme, London Bridge is falling down.
And connects it to finds of human sacrifices in old bridge foundations, like St. Benizet's Bridge in Avignon.
A chilling historical note. Maybe a desperate attempt to ensure structural integrity through supernatural means. Benezet himself became the patron saint of bridge builders.
Weird mix of faith and engineering. Now, flat arches are tricky.
Because they push outwards very strongly at the ends, the abutments. Big problem if the ground is soft.
Which is why you see those long medieval bridges with many arches and piers.
Exactly. Spreads the load, less outward thrust at any one point. Good for weak foundations, but bad for river navigation.
Cast iron arch bridges, like Brunel's at Maidenhead, were successful.
But less common now than beam bridges, and the reason goes back to tension.
Arches need to stay in compression. Beams have tension on the bottom.
Right, so if you have materials good in tension, like steel, beams can be lighter and cheaper for many spans.
Which leaves naturally to suspension bridges. They embrace tension.
Using chains or cables. James Finley gets credit for the modern system, hanging the deck below the main cables.
And the big breakthrough was high-tensile steel wire.
Absolutely. About 10 times stronger than the wrought iron Telford used. Allows spans nearly 10 times longer. That's why we have bridges like the Golden Gate or the Severn Bridge.
And the fact that the cables are made of thousands of wires makes the material's potential brittleness less of a worry.
Yes, redundancy. One wire breaking isn't catastrophic.
Going back to arches, quickly keeping that thrust line inside the arch shape is key.
For stability. Roman semicircular arches were robust. Modern thin concrete arches need very precise shapes to manage that thrust line.
And tied arches or bowstring girders.
That's where you connect the ends of the arch with a tension member, like the string on a bow. It contains the outward thrust within the structure itself, useful if you can't rely on the ground or piers to take that thrust.
Okay, let's talk about beams and trusses structures resisting loads sideways. Tree trunks, masts, bridge decks, roof trusses.
Downwell backs.
All examples. They span a distance and carry load perpendicular to their length, ideally without pushing outwards on their supports.
And the stress pattern inside a bending beam is fundamental.
Compression on the concave side, usually the top, tension on the convex side, usually the bottom, and zero stress along the neutral axis in the middle. And for typical materials, that stress varies linearly from top to bottom.
Yes, for Hookean materials. Unlike masonry, beams are designed to handle that tension.
Which is why efficient beam shapes like I-beams or H-beams exist.
Exactly. Put the material where the stress is highest in the top and bottom flanges to handle compression and tension. Connect them with a thin web, mainly to handle shear forces. Minimum weight for maximum strength and stiffness.
You mentioned shear. Let's touch on that.
Shear is about forces acting parallel to a surface, causing a sliding or distorting effect. Materials have shear strength and shear stiffness, shear modulus.
And this is important for understanding anisotropic materials, materials with different properties in different directions.
Definitely. Like wood, which is strong along the grain but splits easily across it, or cloth.
The source uses a cloth example really well, stiff when pulled along the threads.
But very floppy and easy to distort if you pull it diagonally. That's shear deformation.
Connecting it to dressmaking versus sailmaking, even Victorian corsets as applied tension structures.
Yes. Managing hoop stresses in fabric. Structural principles are everywhere.
Now, a force crucial in aviation. Torsion. Twisting.
Hugely important for wings. The source points to early failures like Langley's aircraft or the Fokker D8 monoplanes. Designers initially focused too much on bending strength.
And didn't fully grasp that wings also twist significantly under air loads.
Exactly. And that twist changes the angle of attack, which changes the lift distribution, which can cause more twisting. It can be unstable.
Anthony Fokker spotted this. The key is the flexural center.
Yes, the point on the wing's cross-section where you can apply a vertical force and get only bending, no twisting. You want the structural flexural center to be close to the aerodynamic center of pressure to minimize twisting under load.
And if the wing isn't stiff enough in torsion, you can get aileron reversal.
A really dangerous phenomenon. You move the aileron to roll the plane, but the twisting force from the aileron is so great it twists the whole wingtip in the opposite direction, reversing the roll. Still a challenge for designers of very fast aircraft.
High torsional stiffness is essential. The source connects this to modern cars, too.
Right. Using the car's body shell as a strong, stiff torsion box, this rigidity allows the suspension to work much more effectively than on older cars with bendy chassis frames. The body itself resists twisting forces.
Let's loop back to compression failure one more time. Buckling, especially for long struts, like leg bones.
Euler's formula tells us the buckling load depends on EIL2, material stiffness E, a shape factor I, second moment of area, and length L.
So to resist buckling, you need high EI relative to length squared. How do engineers increase I efficiently?
Make the column fatter, like Greek Doric columns, or distribute the material away from the center using shapes like tubes, H-sections, box sections. Hollow tubes are often the most efficient for buckling resistance per unit weight.
And sandwich construction. Honeycomb cores.
Another way to get high I with low weight, spreading thin, strong skins far apart with a lightweight core. The source mentions George May's early paper honeycomb, though it struggled with moisture.
And how wood fails in compression is interesting, not just crushing.
It often forms these localized bands or creases where fibers buckle, frequently starting at stress concentrations like knots or holes. It's different from tensile cracking.
And the source suggests rounded shapes might be better at stopping these compression failures from spreading than sharp-cornered box sections. Maybe why bones and branches are round.
Plausible. Nature often finds robust solutions.
And pre-stressing, like in trees. Outer layers in tension, inner in compression.
Reduces the maximum stress reached when the wind bends the trunk, increases its effective strength, like preloading a spring.
All these examples point towards a deeper philosophy of design, why things end up shaped the way they are.
Yeah, the source mentions pioneers like Michell and Darcy Thompson who studied how structures in neutron artifacts seem optimized for their loads and costs, be it money or energy.
Like an underlying logic.
And it reveals interesting patterns. For tension structures, using more, smaller members can actually save weight overall, despite the extra connections.
Like rigging on a ship or muscles spreading out.
Exactly. Reduces peak loads and the impact of heavy end fittings. But for compression structures, the opposite is true.
Subdividing compression members usually increases weight.
Yes, compression structures tend to be more efficient when they are larger and carry heavier loads.
And comparing space frames versus monocoque shells.
Space frames, like trusses, are generally lighter for pure compression, but monocoques, stressed skins, are much better for shear and torsion.
Which explains the shift in aircraft design in the 1930s. From fabric-covered frames to metal shells.
Absolutely. Speeds went up, torsional stiffness became critical for wing safety, and monocoques provided that stiffness even if they were a bit heavier. The trade-off became worth it.
Though lightweight hang gliders might revert to space frames where torsion isn't such a big issue, context matters.
Always. The design follows the function and the forces.
The source even throws in a fun what-if about the pneumatic tire.
Yeah, if it had arrived 20-30 years earlier, around 1830, could efficient road transport have taken off so fast that we skipped the main railway boom? Intriguing thought.
And mentioning inflatable structures, like dracone barges for liquids or even sandbags.
As efficient ways to use thin membranes and tension to contain a load. Very similar to some biological pressure vessels.
Okay, shifting tone a bit. The source calls the 20th century the age of steel and concrete.
And maybe the age of ugliness and age of waste. It links this to the huge energy cost of making these modern materials.
Tied directly to cheap fossil fuels. Tables 6 and 8 really show this starkly.
Looking at structural efficiency per unit of energy used in manufacturing, wood, brick, basic concrete are massively more efficient than steel, aluminum, titanium, even carbon fiber for providing stiffness or compressive strength.
The author argues that holes, cellular structures, like wood, or even Romans using wine bottles in concrete, are a much cheaper way energy-wise to get stiffness than making high-tech fibers.
Nature figured that out long ago.
On aesthetics, the source suggests modern ugliness isn't inherent in industry itself.
But maybe reflects a decline in taste or creativity after, say, 1800 in Britain. An interesting, if debatable, point.
And that functional efficiency doesn't automatically equal beauty.
Right. Pure performance optimization, like in some racing yachts, can look quite sterile. Appearance often comes more from the maker's personality and the heir's values.
And the idea of formalism rules and conventions in design.
Not as a limitation, but as a framework for beauty. Like the rules underlying beautiful old ships, Greek drama, Jane Austen, the Parthenon. You need to understand the rules to fully appreciate the result.
Like knowing cricket rules to enjoy the game, or engineering principles to appreciate a cathedral.
Exactly. And the eye needs a subjective sense of stress.
We need to feel, visually, how the loads are carried.
Yeah. Modern buildings often hide their structure behind thin cladding, which can feel unsatisfying or even unnerving because you can't intuitively see how it's standing up.
Okay, let's turn to when things go wrong. Durability, fatigue, accidents. Lifespans vary hugely.
From minutes for a rocket to centuries for a cathedral, contrasted with arbitrary ideas like the one-hoss shay, designed to last exactly 100 years.
And then there's metal fatigue, that hidden killer.
Cumulative damage from fluctuating loads. The source mentions Kipling and Neville Shute's No Highway, bringing the concept to public awareness. Mr. Honey, the boffin predicting failure.
Which became horribly real with the comet crashes in the 50s.
A landmark investigation by Sir Arnold Hall, painstakingly recovering wreckage from the Med to find the cause.
Fatigue cracks starting at the corners of the square windows. Stress concentrations again.
Proving fatigue could cause sudden, catastrophic disintegration. The source also notes the difference in fatigue behavior between steel, which often has a limit, and aluminum alloys, which might not, making aluminum potentially trickier long-term.
But accidents aren't always fatigue. Early steam boilers.
Explosions were terrifyingly common. Bad materials like cast iron neglect, errors like blocking safety valves.
The source gives some gruesome examples, piling coal on the safety valve lever.
Just unbelievable carelessness with lethal consequences.
And ships capsizing from being top-heavy.
Reducing stability, the metacentric height. The loss of HMS Captain in 1870 is the classic case study.
Fitted with heavy masts for better gun arcs, but it compromised stability.
Fatally so. She capsized in a squall, nearly 500 lives lost. A huge scandal.
And it pushed the Royal Navy faster towards steam power, away from sails on battleships.
A stark lesson that design is about the whole system. Stability is as crucial as firepower or structure.
The source's final thoughts on accidents are pretty hard-hitting. It talks about two levels of cause.
The immediate technical failure and the underlying human element.
And the author is blunt. Maybe 9 out of 10 accidents aren't just random chance. They stem from
What the author calls old-fashioned human sin. Lack of care, incompetence, cutting corners, sometimes worse.
pushing back against excusing errors solely based on environment or upbringing. The anecdote about the workman drilling a hole in a wing spar.
Plugging it, saying nothing, and getting acquitted. The author sees this as reflecting a low view of individual moral responsibility for such actions.
And this connects to the idea of engineering as applied theology.
Because engineers deal with unforgiving physical reality. Gravity doesn't negotiate. Materials break when they break. You can't bribe physics.
So their stuff has to work safely, reliably. Demands objectivity, integrity.
The source uses the intense precautions and psychological strain in an explosives lab as an extreme example of this direct confrontation with unforgiving physical laws.
So ultimately, learning about structures isn't just equations.
No. The source argues calculations are analysis tools, used after the design concept emerges from experience, wisdom, intuition.
The best way to learn is by looking, doing, making.
And breaking things, playing with blocks, Meccano, building models, and loading them until they fail.
Seeing how they fail makes the theory click.
Absolutely. It makes stress, strain, buckling tangible, not just abstract ideas.
So quite a journey, from Babel to buckling, biology to bridges.
Yeah, from the basic physics of forces and materials to the complexity of aircraft wings, the amazing strength of natural stuff, and that undeniable human factor in both success and failure.
It's clear structures are way more than just steel and concrete. It's about forces, energy, materials.
And that interplay between human ingenuity and the often unforgiving laws of the universe. Sometimes elegant, sometimes tragic.
Whether it's a tiny crack causing a disaster or, as the source puts it, historical sin in a design choice. There's always more going on beneath the surface.
Definitely gives you a new way to look at the world around you, the built environment, even yourself.
So here's a final thought for you to take away, building on that human element.
Given how critical human care, competence, and simple integrity are in preventing failures, how should we as a society really think about responsibility, craftsmanship, and accountability, especially now in a world that depends so much on incredibly complex engineered systems?
Something to ponder. Thanks for joining us on this deep dive.